In 1977, NASA launched 2 spacecraft on a 5-year mission to study Jupiter and Saturn. Nobody expected them to last beyond that. No one predicted they'd still be working in 2026, nearly 50 years later, billions of miles past everything they were built to see. But they did last, and when they finally reached the edge of the Sun's domain, the true boundary where our solar system ends and the rest of the galaxy begins, they found something nobody was ready for. The boundary was more than 2 billion miles farther out than every model predicted. Its shape was wrong. The magnetic field behaved in ways no one anticipated, and the space beyond it had properties that contradicted decades of careful science. 2 machines built with 1970s technology quietly proved that we did not understand our own cosmic neighborhood. So what did they actually find out there? Today we're traveling to the very edge of the Sun's reach and finding out how wrong we were about where we live. To understand what they found, you first have to understand what the edge actually is, because it isn't where the last planet sits. The Sun does more than shine. It blows. A constant stream of charged particles pours off its surface in every direction at hundreds of kilometers per second. This is the solar wind, and it carves out an enormous bubble around the entire solar system, a region where the Sun, not the galaxy, is in charge. That bubble is called the heliosphere. It doesn't go on forever. Out in the space between the stars, there's a thin gas, the interstellar medium. Incredibly sparse, better than any vacuum we can make in a lab, but not nothing. And eventually, the Sun's wind pushes out until its pressure exactly balances against that gas. That balance point is the real edge. It's called the heliopause, the outer skin of the Sun's bubble. Cross it, and you've left the Sun's domain and entered interstellar space. Not the whole solar system. The Sun's gravity reaches much farther, out to distant comets. But in terms of the Sun's wind and magnetic field, the heliopause is the border. By the 1990s, scientists had built detailed computer models of this boundary. They ran sophisticated simulations, and they were fairly confident about the answer. They predicted the heliopause would sit around 90 to 100 astronomical units from the Sun, 100 times the Earth-Sun distance. They predicted the bubble would be roughly spherical, maybe with a slight tail. And they predicted a clean crossing. Solar particles fading out, cosmic rays rising, the magnetic field rotating to a new direction, all over a few tidy weeks. The physics was well established. The models were refined. They should have been close. On the 25th of August 2012, after 35 years of flight, Voyager 1 crossed the heliopause. Solar particles vanished. Cosmic rays from the galaxy surged. The spacecraft had left the Sun's bubble and entered interstellar space, the first human-made object ever to do so. But there was a problem. Voyager 1's plasma instrument had failed years earlier, so it couldn't directly measure the one thing that would prove the crossing. The evidence was strong, but indirect, and the debate ran so long that NASA didn't officially announce it until 13 months later. And when they confirmed the distance, it stopped the argument cold. Not 90 astronomical units, not 100. Voyager 1 crossed at about 122 astronomical units, roughly 11 billion miles from the Sun, 20 to 30% farther than the models predicted, more than 2 billion miles beyond the boundary scientists had calculated. That's not a rounding error. It means the balance was off. Either the solar wind is stronger than we thought, or the interstellar medium is thinner, or both. Later analysis pointed toward a less dense local neighborhood, pushing the whole boundary outward. And this matters for us. A bigger bubble is a bigger shield. The heliosphere is what blocks most galactic cosmic rays from reaching the inner planets, so its size shapes the radiation environment Earth has lived inside for billions of years. Then came the shape. Scientists expected a sphere, maybe with a comet-like tail, but basically symmetric. What the data revealed instead was something more like a bullet or a teardrop. The front, where the sun plows through the interstellar gas, is compressed into a blunt nose. The sides are flattened, and behind, a long tail streams out for potentially hundreds of astronomical units. The reason is motion. The entire solar system is moving through the galaxy at hundreds of thousands of miles per hour. From the sun's point of view, the interstellar medium is a headwind, and it squashes the front of the bubble the way air piles up in front of a moving car. So the edge of the solar system isn't a calm, fixed sphere. It's a wind-blown shape, dented and streaming, shifting as the sun drifts through denser and thinner patches of the galaxy over thousands of years. The Voyagers caught a single snapshot of a boundary that is always changing. But the strangest discovery came just before Voyager 1's crossing. In 2012, the spacecraft entered a region no model had predicted, a place where the magnetic field lines lined up and pointed straight outward, perfectly organized, and particles flowed along them in both directions. Solar particles streaming out, galactic cosmic rays streaming in. The field lines were acting like a road, connecting the inside of the bubble to the galaxy beyond. Scientists called it the magnetic highway. Nobody had anticipated that the sun's field and the galaxy's field could link up this way, opening a lane where particles pass freely between two regions that were supposed to be separate. Voyager spent about 2 months on that highway before finally breaking through the edge itself. A structure no one predicted, at a boundary no one placed correctly, on the way out of a bubble the wrong shape. The models weren't just off on the numbers, they were missing entire features. The crossing itself was supposed to be clean, a clear line where everything changed at once. It wasn't. For Voyager 1, the approach dragged out over 2 years of confusing, contradictory signals. And when solar particles finally vanished in 2012, the magnetic field didn't rotate the way the models demanded. That single fact kept scientists arguing for a year over whether it had really crossed at all. The eventual answer was almost funny. In that particular region, the galaxy's magnetic field happened to point in nearly the same direction as the sun's. Pure coincidence. So the expected dramatic rotation simply didn't happen. The two fields were already aligned. 6 years later, Voyager 2 gave the clean measurement its twin couldn't. On the 5th of November 2018, it crossed at about 119 astronomical units, and this time the plasma instrument still worked, capturing the density jump directly. And here's the puzzle that remains unsolved to this day. Both probes crossed at almost exactly the same distance, despite traveling in different directions and during opposite phases of the sun's activity cycle. By the models, they shouldn't have. Nobody can fully explain it yet. And then Voyager 1 detected something that shouldn't have reached it at all. Out in interstellar space, beyond the edge of the bubble, its instruments picked up waves, pressure waves rolling through the interstellar plasma. Scientists called them tsunami waves. Here's what causes them. When the sun has a major outburst, a coronal mass ejection, a violent burst of solar wind, that pulse races outward through the heliosphere. When it slams into the heliopause, it hits like a hammer and launches a shock wave out into the interstellar medium beyond. Months, sometimes years later, that wave rolls over Voyager, and its instruments feel it pass. The first arrived in late 2012. More followed over the next several years, and each one traced back to an eruption on the sun that had happened long before. It means the sun's reach doesn't stop at its own boundary. Its storms echo outward as shockwaves into the space between the stars, farther than anyone thought the sun could touch. There's one more thing these spacecraft did, and it wasn't a measurement. In 1990, before Voyager 1 began its long climb toward the edge, it turned its camera back toward home and took a family portrait of the solar system. In one frame, Earth appeared as a single point of light, less than a pixel, hanging in a scattered beam of sunlight. The astronomer Carl Sagan looked at that image and saw everything. Everyone who ever lived, every war, every love, every triumph, and every loss. All of it on that one tiny dot, suspended in a sunbeam. And the spacecraft that took that picture kept going. It crossed the heliopause. It entered interstellar space. And from out there, at the true edge, that pale blue dot is smaller still. The whole solar system just a bubble. The sun just one star among hundreds of billions. The Voyagers went to the edge to measure a boundary. What they really showed us is how much we still don't know. That even our own doorstep held surprises we couldn't have imagined. Two machines, built by hand, launched before most people watching this were born, are still out there right now, flying through the dark beyond the sun's protection, sending back whispers from a place no one else has ever been. And they proved that the edge of everything we call home was never where we thought it was. Thank you for watching. If you'd like to keep exploring the universe with us, subscribe to Cosmic Lab TV. There's a new journey every week.